Welcome to APA's weekly webinar series. This webinar is being co-sponsored by the Center for Campus Fire Safety. My name is Billy Zadig, Standards and Codes Administrator for APA. Just a couple of housekeeping items before we get started. The webinar will be posted to the APA webpage later this afternoon. You'll receive a follow-up email in the next couple days with the link to the webpage where all webinar recordings are housed, as well as the link to our upcoming webinars. We have webinars planned out through 2020, and many are open for registration. All attendees are in listen-only mode. Please type your questions in the chat box, and they will be answered in the order they are received. If we run out of time and we still have questions, responses will be sent directly to the person asking the question by our presenter. Professional continuing education credits and AIA CLUs are being offered. For AIA certificates, please send an email to Billy, B-I-L-L-I-E, @APA.org with your member number. If you did not indicate you wanted a certificate when you registered, just send me an email. For ICC re-accreditation credits, please follow up with Kathy Tabor at CCFS. If you have more than one person attending this session from a central location, please contact me so everyone gets credit for attending. At this time, it's my pleasure to turn this over to Justin Daniels, Fire Marshal, Emergency Management, University of Oklahoma, and President of CCFS. Justin, take it away.
Thanks, Billy. Just making sure you can hear me. Everybody good?
Yep.
Okay, good. Thanks, Billy. The Center for Campus Fire Safety and APA are great partners. We work together a lot on these things. I'm sure some of you have participated in many of these that we've done in the past. And we were just talking that it sounds like a lot of us are going to be working home for the foreseeable future. And so we're going to continue to do these and provide an opportunity for folks to learn remotely. Most of you are probably familiar with CCFS, but if you're not, we're a nonprofit organization which recognizes campus fire marshals and campus fire safety officials at colleges and universities all over the United States. We have a library of online resources that are free. We do a regular newsletter, and our annual forum is every year in November. This year we will be in New Jersey, recognizing the 20th anniversary of the Seton Hall fire. And we're expecting, well, hopefully by November, we'll be able to continue and with business as usual. And this year's forum in New Jersey is going to be very big for us, and we're really looking forward to it. You can visit us at campusfiresafety.org for all the information on our organization. And next slide, please. So next, I want to introduce our presenter, Chris Unangst. He's a PE for Jensen Hughes. Jensen Hughes is another great partner for the Center for Campus Fire Safety and APA. Chris is a process safety consultant at Jensen Hughes and a certified safety professional with a background in process, dust, and chemical safety, and regularly conducts facility safety assessments, dust hazard analysis, and process safety consulting. And Chris joined us at our annual forum this past year in Atlanta. This topic was very big and went over really well, so we wanted to continue this discussion. So with that, I'll turn it over to Chris.
Thank you, Justin. So I'm going to go through a lot of information today, and I'm going to try to do it in the time that we have. We will be engaging all the participants, so be ready to answer some questions. Billy will put up some polls for you. They're multiple choice, so take a stab at it. We're not grading you. We just want to try to facilitate some engagement with these webinars, especially in this day and age where a lot of us are now working from home. So a brief course description here. As additive manufacturing, AM, becomes more cost effective and widespread, Maker spaces and associated equipment are being installed onto college campuses and educational facilities. There are inherent combustible dust hazards in additive manufacturing. So that's what we'll be talking about today. Some of the learning objectives that we have. We're going to identify the 5 components of a combustible dust explosion. We'll help you understand building code requirements for additive manufacturing. We'll identify some of the unique fire and explosion hazards associated with additive manufacturing. We'll describe some of the design-based protection methods available for additive manufacturing, and then also some of the operation-based protection methods. But to start, we'll define additive manufacturing. So it's the process of joining materials to make parts from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing or formative manufacturing methodologies. There are some other terms that are used: additive fabrication, freeform fabrication, additive techniques, additive layer manufacturing, and those are sometimes used interchangeably with additive manufacturing. AM machines have a lot of benefits. They don't require expert machinists to actually make a part, and they're typically it can be much quicker to make a part, or if you're doing some type of research and development, you can actively test multiple different prototypes in the time that it would, it typically took maybe to make one prototype. So that, and then there's many other benefits to them. Types of additive manufacturing machines. There's a number of different types: vat photopolymerization, material jetting, binder jetting, material extrusion, sheet lamination, directed energy deposition, and the one that we'll be focusing on today is powder bed fusion. And within powder bed fusion, there's a number of different methods to use. You got direct metal laser sintering, electron beam melting, selective heat sintering, selective laser melting, and selective laser sintering. These can use metal powders. Aluminum, titanium, chromium are some examples. Many of these are combustible dusts. You can also use powdered plastics, but what we'll be focusing on today is metal dust. So here is just a brief example of laser sintering. And so what you have is a powder delivery system. So you, on the left side of this orange line, is the additive manufacturing machine setup. You have bulk powder on one side. It is slowly pushed up by a delivery piston, and a roller will take that powder over to the fabrication side, deposit a thin layer on that fabrication side. Once there, you'll have, in this case, a laser beam that will sinter the powdered particles, join them together. And it will do that based on the 3D model. And once that layer is completely finished, the roller will, the delivery piston will move up, the roller will put another layer of powder down, and you'll repeat what you just did. And you'll do that for many, 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 many layers until you finally have a finished product. So here's our first question, and Billy will put out the poll for you guys. Combustible dust. At what particle diameter is combustible particulate classified as dust? Please take a second, put down A, B, C, or D. A is 1,000 microns, B is 750 microns, C is 500 microns, and D is 420 microns. I'll give you a hint here. used to be one answer and now it's another one, and they're relatively close in size. So I'll give you 5 seconds here, and Billy will close out the poll.
19% said 1,000, 14% said 750, 43% said 500, 24% said 420.
Okay. All right. So the definition of combustible dust is a finely divided combustible particulate solid that presents a flash fire hazard or explosion hazard when suspended in air or another oxidizing medium. Dust traditionally were defined as a material 420 microns or smaller. But for consistency with many standards that are out there, 500 microns is now the appropriate size criteria. To give you some perspective, ordinary granulated sugar is about 75% sub 420 microns. Metal powders used in additive manufacturing typically meet this criteria. So components of a combustible dust explosion, and we'll build up to the explosion part. We'll start with a fire hazard. So a fire hazard has 3 main components: fuel, so this is your metal powder, metal dust; an ignition source, it could be multiple things. It could be electrostatic discharge, it could be electrical, it could be the laser that's in the actual equipment, and oxygen. A deflagration hazard is all of those 3 components that a fire hazard is, except you have dispersion. So you have the dust dispersed and suspended in air or an oxidizing medium. And then an explosion hazard is a deflagration hazard, but it's now confined. So you have the fuel, which is your metal dust, an ignition source, oxygen, dispersion, and then you have it enclosed in a vessel. An explosion hazard is the potential for a rupture of a closed vessel. Fire hazard would be when you have a layer of powder on the ground and it's ignited. And then a deflagration hazard is a dust cloud is dispersed in air. However, it's not within a vessel, and then you have you could have a deflagration. Flash fire and deflagration are kind of used interchangeably in industry. Just to give you a baseline here, they do have different definitions according to NFPA codes. A flash fire is a fire that spreads by means of a flame front rapidly through a fuel such as dust, gas, or the vapors of ignitable liquid without the production of damaging pressure. Similarly, deflagration is the propagation of a combustion zone at a velocity that is less than the speed of sound. An explosion is the bursting or rupture of an enclosure or container due to the development of an internal pressure from a deflagration. Another question, and Billy will put up this poll for you guys as well. For building codes, how much combustible dust can I use or store based on the IBC 2018? A is 100 pounds, B is 50 pounds, C is 20 pounds, D, the value is not specified. So this is in reference to table 307 of the IBC, and it has to do with maximum allowable quantities, MAQs. So we'll take a second, 5 more seconds here to finish up the poll, and we'll see what kind of answers we got back from everybody.
12% 100 pounds, 25% 50 pounds, 18% 20 pounds, 45% value not specified.
Okay. So it is not specified. In that table 307.11 for combustible dust, it says C note Q. Well, what is note Q? It says where manufactured, generated, or used in such a manner that the concentration and conditions create a fire or explosion hazard based on information prepared in accordance with section 414. So what you will want to do is prepare information according to section 414. And what 414.1.3 really says is that you should do a dust hazard analysis. And we'll touch on that later in this presentation. What is a dust hazard analysis and what does it consist of? But the report, so this dust hazard analysis report shall be prepared by a qualified person, firm, or corporation approved by the building official and provided without charge to the enforcement agency. So if you do not prepare that report for the AHJ, you don't account for fire and or explosion hazards, then the occupancy would be a group H2. You also need to account for water reactivity. For dusts that are water reactive, such as titanium, that's class 2, if storing more than 50 pounds in your maker space or adjacent to your maker space, that occupancy would be an H3. With a water reactive dust, sprinklers are not allowed. And depending on local codes and the AHJ, an approved automatic fire detection system might be used. So if you want a fully sprinklered building, but you can't put sprinklers where you have a maker space because you have water reactives, what do? Well, the IBC addresses that. The provision of an automatic fire detection system preserves the building status as a fully sprinklered throughout. So it is still eligible for all code alternatives, exceptions, reductions, and increases that are permitted in fully sprinklered buildings. You should have Class D portable or wheeled extinguishers listed for use on combustible metal fires. They shall be provided and distributed in accordance with NFPA 10. Now, fire extinguishers on combustible metal fires should be used with caution. It's best to fight an incipient fire by ringing it with a dam of dry sand or dry material that will not react with the metal being extinguished. Application of a dry extinguishing agent shall be conducted in such a manner as to avoid any disturbance of the combustible metal dust, which could cause a dust cloud. So if you take a fire extinguisher, aim it very close right to the center of that fire, what you could end up doing is creating a flash fire hazard, and that's a greater hazard than what you started with. So the application of fire extinguishers, you should really conduct training on that, and you should do it so as to not disturb or spread the combustible metal powder. And then one more item there is the physical barriers. So if you have a dust flash fire hazard area, you should have a 1-hour fire resistance rating. So protection methods for 3D printers. So this is your dust hazard analysis is the industry standard. DHA is what you'll hear me refer to it as. It's an evaluation of material hazards, the building hazards, and equipment hazards, and then also an evaluation of administrative controls and recommendations for those. And we'll touch on each one of those bullets the remainder of this presentation. So here's another question. Material hazards. What NFPA standard would be best to start with to get information on combustible dust? NFPA 654, NFPA 101, NFPA 652, or NFPA 30? I will give you a hint here. It may start with a 6. And then Billy, if you want to give everyone 2 more seconds, we can close it up and see what we get from the audience here.
NFPA 654, 22%, NFPA 101, 7%, NFPA 652, 58%, NFPA 30, 13%.
Okay. NFPA 652, Standard on the Fundamentals of Combustible Dust. So that is the go-to, and from there, it will direct you towards other combustible dust standards. And there's a number of them out there. NFPA 652 is NFPA's attempt to kind of consolidate all the different combustible dust standards that are out there. NFPA 484 is the standard for combustible metals. You'll hear me cite that throughout this presentation. It has a section devoted to additive manufacturing. NFPA 654 is another good one. 499 is good for hazardous area classifications. 68, standard on explosion venting. 69, standard on explosion prevention systems. Additive manufacturing machines often will have explosion prevention systems, and they should be compliant with NFPA 69, as we'll discuss later. NFPA 70 is the NEC, 79 electrical standard for industrial machinery. So factors used in determining material hazards. So every metal dust powder, metal powder has its own characteristics, and testing of each of your powders will help develop that baseline for how you should properly protect your A&M machines, building, and people. We always recommend to get the powder that you're using in the additive manufacturing lab, the maker space, whatever you call it, get it tested before bringing it on site. There's combustible dust testing out there that will give you a good idea of the hazards that powder poses. So up here, you'll see there's a couple examples of aluminum here, and they all have somewhat different values of their characteristics. They're not all identical. So that kind of further exemplifies the point, is to get your specific powder tested, or ask the manufacturer to provide you the data that of what they did to test it. But real quick, the KST is your rate of pressure rise. Your Pmax is the maximum pressure produced during the deflagration. So that tells you kind of the severity, how quickly will pressure rise, and how much pressure will be developed.
How are you?
Good. The cloud ignition temperature is the temperature at which a cloud of dust will be ignited if exposed to. The MIE is your minimum ignition energy, so how much energy it takes to actually ignite a dust cloud. Your MEC is your minimum explosible concentration. So that is how much dust needs to be suspended in air for it to actually be an explosion hazard or deflagration hazard. And then you're limiting oxidant concentration. So that is the concentration for which you should stay below to eliminate the possibility of being an explosion hazard. So you can see there it varies, and it also will vary based off of what inerting agent you use, whether it's nitrogen or carbon dioxide or argon. So we'll use the material hazards to kind of work through the building hazards and the equipment hazards. So for building hazards, you want to exercise ignition source control. Have a hot work policy in place, no smoking policy. You may also want to consider classified electrical equipment, and then have electrostatic discharge controls in place. You also want to prevent hazardous fugitive dust conditions. Have your equipment enclosed, dust tight, use small quantities of powder, and have a good housekeeping program. And then there's some HVAC considerations as well. So we'll go, next question here is classified electrical equipment. Where can I get more information about classified electrical equipment? NFPA 70, NFPA 499, NFPA 77, or NFPA 1. So if you all take a couple seconds and choose A, B, C, or D. So we're looking for electrical equipment. And there may be two right answers here in this case. So Billy, if you want to close the polls, and we'll see what the audience chose.
NFPA 70, 77%, NFPA 499, 8%, NFPA 77, 15%, NFPA 1.
Okay. So NFPA 70 is your go-to. Article 500, hazardous locations. So class 2 locations are those that are hazardous because of the presence of combustible dust. Within this class 2 location, your metal dust would be classified as a group E. But there's another place. So those that answered NFPA 499 are also correct. That's your recommended practice for classification of combustible dust and of hazardous locations for electrical installations. NFPA 499 is very useful because it contains some diagrams, and who doesn't love a picture, of how to classify rooms or areas. Here in this one, the gray area is a class 2 division 1 group E, and the striped or the lined area is class 2 division 2 group E. Although there's funny is there really is no such thing as class 2 division 2 group E. It's just dust tight equipment. And of note is that housekeeping can reduce or eliminate electrical area classification for a location where combustible metal dust is present. NFPA 484 recognizes this, stating electrical equipment upgrades can be costly, and users might be better focused on preventing fugitive dust from escaping equipment, so keeping your equipment enclosed, and reducing accumulations, minimizing accumulations, so that a hazardous area wouldn't exist. Dust ignition proof. So this is your NEMA 9s. This protection technique shall be permitted for equipment in class 2 division 1 or 2 locations. Dust tight equipment is only approved for equipment in class 2 division 2 locations. With classified electrical equipment, there will always be a T code. And that's the temperature marking shall be less than the ignition temperature of the specific dust to be encountered. So if the ignition temperature of your dust is 200 degrees Celsius, you would not want to use an electrical equipment that has a T code of T3 because it could reach 200 degrees C. You would want to use a T code that has a maximum temperature below that of which your dust is. So, you know, a T4, T5, etc. And here, the cloud ignition temperature, you can see there. So if you get your dust tested and you find that your cloud ignition temperature and or layer ignition temperature is X degrees Celsius, you'll want a T code that will not reach that, that number. Static electricity, another important topic. Oop. Oh no, I gave it away for you. What is the static spark energy a typical person can produce? And is this above the minimum ignition energy for any combustible dust? So we have a couple options there. If you're paying very close attention, you may already know the answer. So A is 50 millijoules, B is 100 millijoules, C is 25 millijoules, and D is 0 millijoules. Y'all take a brief moment and mark one of those down. And then let Billy close it and see what we got, see what we came up with.
Apologies, I forgot to unmute myself. 50 MJ, 33%, 100, 34%, 25, 33%, and no one said 0.
All right, yeah, because everybody knows that they've sparked someone before when they rub their feet on the carpet or whatever it may be. Okay, so the, oops, lost it here. The maximum reasonable discharge energy from a person is estimated to be approximately 25 millijoules. So to put that in perspective to the dusts that are being handled, titanium powder has an MIE of 18 millijoules. And nanoparticles, which can be used in A&M machines, so have MIEs less than 1 millijoule. So what does that mean? It means that a person that generates static electricity could possibly serve as an ignition source for combustible dust. Next question here, still about static electricity. So when you're transporting, and go ahead, we've got yes or no as the options here. This is the easy one. When transporting dust shipments within containers to a lab on a cart, so you have them delivered, someone goes out and gets them, do the materials that the cart is made of matter? Yes or no? And we'll give everyone a couple seconds here and then we'll close it. And Billy will let us know what we come up with.
%, said yes, 8% said no.
All right. And they do matter. Awesome. Yes, for especially sensitive dusts, carts should be made of conductive material with non-static wheels to prevent static charge buildup and sparks. So what does this mean for your design? You should have a dedicated grounding system for equipment. So every additive manufacturing machine, 3D printer that's handling combustible dust, combustible metal dust, should be connected to a dedicated grounding system. Personnel may also need to stand on static dissipative mats and adhere to bonding and grounding requirements. So that may mean static dissipative footwear, wrist straps to bond yourself to the actual 3D printer. Flammable storage cabinets must also be certified for storage of combustible materials and must be grounded as well to prevent static accumulation. Another important topic, housekeeping. So fugitive dust shall not be allowed to accumulate to a level that obscures the color of the surface beneath it. So if you have fugitive dust laying on a surface, you should be able to see what color that surface is below it. It's imperative to create a housekeeping plan and then also to use appropriate methods. So in this first picture, sweeping is going on, but you'll see a little bit of a dust cloud right in front of it. Sweeping is the preferred method, sweeping and or brushing combustible dust, combustible metal dust, but you should do so in a manner that does not create, that doesn't disturb the dust and create a dust cloud like you see in the picture right there. The second picture is your typical shop vac, and shop vacs should not be used when collecting metal dust. The vacuum should carry some type of certification, UL, ATEX. You'll often see these as EX rated vacuums. They should only be used for small amounts of fugitive dust, and then the large spills should be gently swept up using conductive or non-sparking scoops. What you'll want to use is a natural fiber brush or broom. A couple notes quickly on HVAC. The HVAC ductwork and associated equipment should be checked regularly for dust accumulations. For metal dust, it's not as much of a concern as, say, a less dense dust, but nonetheless should be checked. And then makeup air for building or heating or cooling shall have a dew point low enough to ensure that no free moisture can condense. That's critical for your water reactive metals. A 3D printer, your AM machine, is a fire and explosion hazard. Hence why processes are typically done under an inert environment. It has all the elements there, and so if you take out the actual oxygen, then you don't have that explosion hazard and or fire hazard. So oxidant concentration must meet requirements of NFPA 69. So that goes back to your material hazards and looking at your limiting oxidant concentration. That's what you get it tested for, so that you know that the 3D printer or AM machine is operating below a level that ensures that you have a degree of safety. Another consideration there, since you are using inert gases within those 3D printers and machines, that you may want to install oxygen monitoring in the actual room that it's contained in. And another consideration is if you're using argon, that's heavier than air, and you may want to consider low-level HVAC intakes. Passivation, so electron beam interaction with metal dust can create vaporized metal. This is especially true for air cleaners within your 3D printers and machines. Upon servicing these air cleaners, the dust accumulated on them is hazardous. So say you've got a filter inside your 3D printer, you open it up, to clean it. When you open it up, you expose it to a lot of oxygen, and you could potentially create a hazard there. So it's recommended that you have a residual oxygen level below the LLC to enable that slow passivation of particles. So a small amount, a couple percent of oxygen within that equipment will help when you actually have to perform maintenance on it. Custom 3D printers. This is the face I make when I hear about custom 3D printers in a makerspace or lab. I have so many questions. Originally, 3D printers and machines didn't have too many certifications with them. As of late, you can start seeing some UL ATEX certifications. Some other questions to ask for these custom 3D printers is, has the machine been reviewed for mechanical and electrical appropriateness? Does it meet electrical requirements? If you have a purged enclosure, it should meet NFPA 496. And does it meet the NFPA 69 requirements for oxidation concentration reduction? So when a part is finished from a 3D printer or additive manufacturing machine, there's going to be some powder left over on it, maybe in internal cavities. That part should be gently rotated prior to its removal to allow that loose powder to be extracted. The part should be held in a position that minimizes the free fall distance from the part to the floor of the actual print chamber. And then you should use natural fiber brushes or conductive bonded and grounded tools to clean that part before putting it into, say, a blast cabinet. The blast cabinet can change particle size and remove oxide layers and increase the exposability of particles. If you have a dust collection system attached to that blast cabinet, you should have the appropriate precautions in place. That dust collection system should preferably go outside and have explosion protection and isolation. Administrative controls. So the first thing you can do is have a dust hazard analysis conducted. And then internally, and if you could do that internally as well, internally also do a JHA, job hazard analysis. Should have good work instructions for material handling and storage, a robust housekeeping policy, conduct inspection, testing, and maintenance, and have some management systems in place. So job hazard analysis may be required for operators of AM machines, staff, faculty, or students. NFPA 484 requires organizations working with metal dust to conduct and document a formal PPE assessment for employees working in areas where flash fire hazards exist. So in that evaluation, you want to look at the tasks, every task that's done, potential thermal hazards that are associated with that task, assign some qualitative risk, and then determine what PPE mitigation measures are needed to address that thermal hazard. Some PPE recommendations. So there's recommendations for general health and safety, and then also combustible dust. For general health and safety, shoes you want to be slip resistant, safety toe protective. You want goggles rated for dust protection, Z87 D4 or D5 if you're working with very fine dust. You should conduct an industrial hygiene study to determine the appropriate respiratory protection, and then you should have material handling gloves. Specifically for combustible dust hazards, your shoes should be anti-static or with conductive soles, using your static dissipative floor mats. And for your hand and wrist static dissipative gloves and wrist straps. And then for your actual outer garments, it should be non-combustible or flame resistant. Also able to dissipate static electricity. Wool, silk, or synthetic fabrics should not be used when handling metal powders, metal dust. And then if you choose to go with flash fire resistant clothing, reference NFPA 2112, and there's some guidance in how to choose the right flash fire resistant clothing in NFPA 2113. You should have a formal training program for personnel involved with A&M processes in the presence of combustible dust. NFPA 484 requires the employer to certify annually that the training and review have been completing. I'm not going to go through each one of these points. You guys can reference these afterwards, but essentially, especially in the collegiate environment where you don't maybe have an employee working there for 10 years, it's critical to train everyone as they come in. You know, training on an evacuation of the work area, what hazards are there, and how to prevent those hazards from creating an incident. Equipment operation, and the importance of housekeeping in minimizing fire and explosion hazards. And then what housekeeping methods you should use, the appropriate housekeeping methods. Management of change. So NFPA 44, written procedures shall be established and implemented to manage proposed changes to materials, technology, equipment, procedures, and facilities. So you're in charge of a lab and you're using one metal powdered material, and now you want to use a new one. Well, you need to evaluate before bringing that new metal powder into the lab. You should evaluate it, one, get it tested, and two, put together what's here, a technical basis for the change. What safety and health implications are there? Maybe this new powder has a lower ignition temperature or has a lower MIE. Whether the change is permanent or temporary, modifications you would need to make, what training you would need to conduct. And then someone should authorize and own kind of any changes that are made within that makerspace or lab. And then inspection, testing, and maintenance program. So NFPA 484 recommends to keep all records of maintenance and repairs performed. And then the inspection, testing, and maintenance program should include ITM, for short, acronym, fire and explosion protection and prevention equipment. So making sure that's working properly, your inerting system is working properly. Interlocks in the event that you lose your inerting system, your equipment shuts down, all of that is working properly. Any dust control equipment that you have should regularly be inspected and maintenance performed on. Housekeeping, doing housekeeping checks, making sure everybody's following the program. Identifying potential ignition sources, maybe it's electrical equipment, maybe the lab's classified, is a classified area and someone is bringing in their cell phone or some other electrical equipment that should not be, or is not rated for that environment. A big one is a continuity check on grounding and bonding systems. A formal continuity inspection program that requires continuity checks on at least an annual basis, as well as any time equipment is moved, sits idle for an extended period, or has any preventative maintenance or repair done on it. That's critical. And then also resistivity testing of static dissipative footwear and conductive floors were required. Especially with footwear, you can get buildup on the bottom of it, which will make it not perform as it was designed to. So you want to make sure, to prevent those electrostatic discharges, and also making sure you got that bonding and grounding. So that's it in a nutshell. We went through a dust hazard analysis, the different types of hazards that would be evaluated there, material hazards, building hazards, equipment hazards, and then a brief discussion on the different administrative controls that you should put in place where you have these additive manufacturing machines. We'll open it up to questions, and if we don't get to everyone's questions, as Billy said earlier, I will get back to you following the presentation.
We have a few questions that came in for you. Are there maximum and minimum explosive limits for combustible dust like there are for gases? That's
a great question. They're not, the upper limit is not quantified as it is for every material, as you would for like flammable liquids and flammable vapors. There is, but you typically don't see that as often with combustible dust. And it's not for every dust.
Next question. Why negative median D for aluminum?
Why? That was an approximate. So that wasn't a negative. It was just an approximate diameter.
Okay. This presentation addresses metal 3D printing. Are there any concerns facility managers should have for common plastic filament 3D printers in labs and offices?
Yes. If that's coming in as a powdered material, plastics, depending on what it is, but high level, they could be considered a combustible dust. And a lot of this kind of same, a lot of this would also apply to those plastic dusts as well, except for the water reactive part.
Okay, thank you. Under what conditions are fire sprinklers allowed at an AM facility?
It's only when, really it should be when the hazard, so does not having sprinklers create a larger hazard than having sprinklers? So you really have to weigh the pros and cons of will a sprinkler, could you have such a hazard that not having a sprinkler there be the greater hazard than actually having a sprinkler in the room? Is something that you need to consider.
Okay. Should the HVAC of the metal 3D lab be isolated from the rest of the building general HVAC system?
Yes, generally it should have its own dedicated system.
Okay. Is the DHA a requirement or a good practice? Who ensures that facilities are doing this outside of internal personnel? Is there an auditing agency?
There isn't an auditing agency. In most cases, it falls under OSHA. Some AHJs are aware of the requirements, and this highly depends on your local codes. It depends on the adoption of NFPA 652 and NFPA 484. NFPA 652 current edition requires all facilities handling combustible dust have a DHA by September of this year. It depends also if your local, your local codes that are applicable to you adopt NFPA 652. What edition do they adopt? Same thing with NFPA 484. But per building code, It is gradually being adopted and then also applicable now. And it also depends, on the AHJ, if the AHJ is aware of the need for DHAs. There's been a push out into the community of kind of educating AHJs of these hazards and what needs to be done. So it's gradually coming around.
Okay. In answering another question, you mentioned having a dedicated HVAC system. Would using the general building supply air but having a dedicated exhaust for 3D printing be acceptable?
Yes and no. It's highly dependent on what you're working with in that area. Especially for water reactive powders. And if you're keeping that dew point temperature where it needs to be. So yes and no, sorry. If we can, I can give you some more detail on that with a follow-up.
Okay. Is there a recommended location to place a 3D metal lab, bottom floor of the building, etc.?
Yeah, typically, the best way would be kind of like as just its own building. But if you're going to put it in a building, then you put it on the bottom floor, and then also on the, not in the center of the building, on the side of the building, or as an attachment to an existing building.
Thank you. You mentioned a 1-hour fire-rated firewall to separate a 3D metal area. Is that the minimum rating?
Yeah, that's the minimum per NFPA 484.
Okay, well, that's all the questions we have. Oh, one more just came in. Can a room be used for AM? Can our room used for AM classified as H2?
I'm sorry, can you repeat that one?
Can a room used for AM be classified as H2?
Yes, it can be classified as H2. If you're using powder material, and it's classified as a combustible dust, whether it's a plastic dust or a metal dust, it can be classified as a H2 if you don't properly mitigate and address hazards that are identified in a hazard analysis, dust hazard analysis.
Okay. That's all the questions we have. I want to thank Chris for taking time today to do our webinar. I want to thank all of the people who attended for taking time, especially during this very busy season on the coronavirus, and to let everybody know that we have a town hall webinar tomorrow from 12:30 to 2 p.m. on emerging practices for COVID-19. If you're interested in attending, if you have any questions, just send me an email and I'll get back to you with a registration link. Again, thank you very much for attending. Be safe, and we'll talk soon. Bye-bye now.